Okay, so let's start with the second lecture of Balázs.
Thank you very much. And as far as you see, I already made some dust on the blackboard. But this is actually just the final moment of the previous lecture. I didn't want to spend some time to repeat it. So let me repeat it briefly. What we have. So we are, from now on, and throughout the whole lecture, we are on the plane. We have a finite collection of affine maps of the plane. We always assume that these matrices are contracting, so all these functions are contracting. The norm is at most 1. We want them to be invertible matrices, and we want two other properties, namely that this finite collection of matrices shall be strongly irreducible, which means that there's no finite collection of subspaces which is preserved by them. And we also want them to be proximal, which means that we are actually in the self-affine situation. So there is a matrix product, a finite matrix product here, made by these matrices, such that it has two different eigenvalue in modulus. Okay, that's our setup. We have our symbolic space, which is the two-sided symbolic two-sided full shift. From this two-sided full shift, we have a natural projection. The natural projection depends only on the positive coordinates of my two-sided infinite words. And this is just the natural projection, the natural coding corresponding to my function. Right? Sigma is the usual left shift operator. There's no change. And we define here a Bernoulli measure on our symbolic space. Okay? With probabilities pi, or the probabilities shall be positive, otherwise we are just reduce ourselves, so we can assume it without loss of generality. And then, by Oszalegyet's multiplicative ergodic theorem, we know that that's not what we know. Okay, what we know is that these two conditions, the true strong irreducibility, the proximality, via a theorem of Furstenberg and Kesten, tells us that the two Lyapunov exponents are different. Then, Oszalegyet's multiplicative ergodic theory tells us that there are two nice measurable functions from the two-sided shift to the projective line, such that one of them, the E, depends only on the positive. The E will represent only on the weak contraction. This is why E, so it's a weak contraction. And F, which is a strong contraction, this will only depend on the negative coordinate. But both of the guys are invariant with respect to this matrix product, and they together gives you back the whole R2. Furthermore, the action, so the growth rate of the matrix products individually on this subspaces E and F, corresponding to my strongest Lyapunov exponent, which is chi2, and the growth rate on E corresponds to the weakest chi1 contraction. Okay? So since we are Bernoulli, now we can really say that then you can think about E and F as random variables and they are independent. Okay? So we can define a Furstenberg measure, which is a push forward via the strong stable direction of my Bernoulli measure. Yeah, and we can define nu, who is our object of study, the self-affine measure itself. Okay? And if you define a dynamics on the product space, which is a product space of the projective circle and your self-affine set, right? Every element here can be represented by this infinite coding. However, if we assume strong separation condition, which we do, when we say that any two different images of my self-affine set are disjoint, then actually this representation here by a positive infinite sequence is unique, right? So I can write here pi of I. Of course, this is just for the positive. This pi doesn't depend on the negative coordinates, but I can define then a dynamical system on it, which means an expansion via the inverse maps in the first and the second coordinate. And in the first projective coordinate, I just modify my direction according to the inverse matrices. And then this product measure, the Furstenberg measure and the self-affine measure, with respect to G, will be an invariant and ergodic measure. And now, what do we want? We want to understand what the dimension of my self-affine measure is. And our first step is to reduce the planar problem to a one-dimensional problem via using the Lapierre-Young formula. How do we do that? We define a projection, which is the orthogonal projection from R2 to R along the direction V. And these directions V will be Furstenberg typical. So we project along the strongest contracting ratios. And what I claim is that in this case, mu and its typical, Furstenberg typical orthogonal projection are exact dimensional. Furthermore, the dimension of mu satisfies this formula. So where I know the entropy, where I know the Lyapunov exponents, so the only thing what I need to understand how the dimension behaves along a typical projection. Okay?
I'm sorry, just silly comment. So chi2 should be a lower index, right? So it's not square. Because previously you denoted...
Did I? Yeah, yes, sure, yeah. I'm always confusing myself with lower and upper indexes. Okay, let's hope that I can keep on track. Yes, but lower index. Yes, this is the largest contracting ratio, and this is the smallest one. So this is the weakest contraction, this is the strongest contraction. Yes.
And I'm getting confused with all these measures. Could you please remind mu f is where does it live?
Mu f, yes, okay. So mu f is lives on, so is a probability measure on the projective circle, not necessarily supported on the whole projective circle, but on some nice compact subset of it. And he is not only this strange object pushed forward by this measurable map F, it's also the unique map who is stationary with respect to the following Markov process, that you have some direction V, you toss a coin, it has with probability pi lengths on I, and then on this direction you apply the 8th matrix inverse. So he is the stationary measure of this unique stationary measure of this Markov process. It's not necessarily always unique, of course, but under these two conditions of strong irreducibility and proximality, it will be.
And on which space mu is defined to measure mu?
Mu is defined is a Bernoulli measure, so very usual Bernoulli measure on the two-sided infinite sequences.
And nu it's push forward.
Yes, the nu is just simply the push forward of this new measure, which is the self-affine measure. So satisfies exactly the same equation, but he lives on the plane, and you have exactly the same kind of Markov chain, except for Fi.
So, in different direction, right?
No, this is planar. So this is on the plane, this lives on R2, this lives on the projective circle.
I mean, for mu f, you take AI inverse?
Yeah, sure, yes.
Okay, thank you very much.
Okay.
So it should be Fi minus 1?
No, here, Fi. So what you want is this equation. So whenever you have some test function, there no sum, then yes, so it's a push forward. So yeah. This star is together this new circle Fi inverse, whichever you prefer. Okay? So our notations setup is clear. Good. Now let's try to do our best. So let's suppose that this is where my self-affine set lives. If I want to understand and if I want to say that this nu is exact dimensional, what do I want to understand? Well, I take a typical point here and I take a ball. Right? This is a ball around the typical point with radius r. And let's see how the measure of this ball decays. But first, instead of understanding this object, we need first to understand how the stripes are decaying. And a stripe will be chosen not according to any direction, but f of I. Okay, so what is a stripe? Well, Fi is my strong stable direction. If I project my measure along this strong stable direction, then I end up here. So what does a stripe represent? The stripe is actually representing what's the measure of the of a ball of the projection. So I can introduce a so-called transversal ball on pi I, and let me introduce a capital notation, a capital pi of I instead of lowercase pi of I, just for further confusions, because I want this projection to work not only on the plane and not only on the RP individually, but together, right? So it projects the negative coordinates or typical element to the projective circle and this one to the plane. So if I'm looking at exactly this two-sided sequence, now it begins to play a role that this is indeed a two-sided sequence. Then the transversal ball with radius r should be all the planar points, all the points on the plane, such that if you take the orthogonal projection of this point, little pi of I, and you take the point, the orthogonal projection along Fi of this y, this distance should be at most r. So it indeed describes this stripe, where the two sides of this stripe is parallel with Fi, and it has width 2r, right? And on the center line, this little pi of I is lined. Okay? Unfortunately, this is not the best object what we want to study, because if you begin to iterate via your G-map this stripe, then one good thing happens. Namely, what happens if you iterate? So if you apply to Fi, Ai not inverse, right? It just goes to F sigma I. That's a good one. So you are somehow preserving along the G-map the strong stable direction. But what behaves badly is its width. Its width begins to play a very stupid game because this width, this orthogonal line to Fi is not invariant. But there is one guy who is invariant, who might help us, is this E of I, right? Who depends on the point. Of course, here it would point to some other direction, but yes?
Sorry, Balázs, you have these lines which are the unstable direction.
Yes.
So it's like a line field around each image of the sequence. Yeah?
The EI, yes. You can imagine, yes, the EI as a kind of tangent bundle on the self-affine.
at each EI you take this direction and you look.
Yes. For each individual center, I mean almost every center point, I will have my EI direction. And the actual transversal goal is, I would like to work with, is this stripe, where instead of knowing that the width of this stripe is R, but I want to know that the part of this stripe, the intersection with EI, has length R. This makes my life much easier. So it's exactly the same pi I, except that you need to take the sine of the angle of EI Fi times R. That's very good. Because, okay, this can be arbitrarily small. This can even go to 0 when I iterate them, except that, okay, there is a lack of information, because except the angle cannot converge to each other faster than exponential. By exponential speed. They can only converge sub-exponentially. Basically, this means that we don't care about this when we are checking exponential rates. Okay, so what does this mean? So we have these good type of stripes. At least we have some kind of good two invariant subspaces along the iterations. Let us check what happens with that part of this stripe. Namely, let me define the natural partition on this space. Namely, what's the natural partition? The natural partition will be only a finite collection of elements, pi of I, such that on the projective circle I don't care, but this denotes the first level cylinder set such that I is in. And there only just the positive coordinates matter. So my question is, what happens with this intersection? So take this little transversal ball with radius r and look at only the part which is inside of the first cylinder set. And now apply on this guy the map G. Namely, you apply the inverse map Fi not inverse. So you apply the matrix Ai not inverse. This direction goes to the F sigma I. Very good. This direction goes to E sigma I. And I also have a good control how the length is changed, because on any subspace, of course, on any one-dimensional subspace, my matrix acts linearly. So if I just blow this guy up by my map G, then I get another transversal ball which is corresponding to the sigma I, and the radii is blown up exactly as much as Ai naught would have contracted on E sigma I. So it is the norm of this Ai naught A sigma I. This is the amount how much this radius blowed up. Is it clear? And that's the big thing. That's the big trick. Okay. Now I have to erase stuff, because what do we want to understand?
What is this point X at the second last line? Right?
X. This one.
The X. Well,
This one is my self-affine set. So this is the whole set. The whole cylinder set whose first symbol is I naught. Okay. So, let me define function RLN of I, which shall be the matrix product of AIL from AIN minus 1 of E sigma Ni, where L is someone who is non-negative and at most N. Well, if L corresponds to N, then this is just 1, okay? By convention. Then there is no product in the business. Okay? And what do we want to check? What's the new measure of the transversal ball centered at Pi with radius R from 0 to N of I? So this is basically the length on EI of my nth cylinder, roughly speaking. But on one hand, again, take the log, take the R0N. Let me recall another notation. This is my logarithm. Okay? So, recall that since we are working with a stripe, it actually gives you what's the local dimension. So, if I take here a limit as n goes to infinity, it must then converge to the local dimension of the orthogonal projection along Fi of my measure nu at the point, the orthogonal projection of pi of I. Right? So this will give you the local dimension of the projected measure. Here, let me introduce a telescopic sum. What telescopic sum? Say this is log nu of this little transversal ball of pi of sigma Ni of 1 plus a sum L goes from 1 to maybe up to N, should be logarithm of the ratio, the transversal ball at sigma L minus 1I or L minus 1N. Let me not repeat the I always, okay? Still the same I divided by the new measure of this little t transversal ball, sigma Li or Rn. Okay, still divided by log R0N. Okay, so actually the difficult part is not so hard to see, that is this one, but it's also not so difficult. This is not so difficult because if you divide by 1 over n, and this is what we want to do, divide here by 1 over n, divide here by 1 over n, and divide here by 1 over n, then this guy, of course, by definition, look at here, product from 0 to n minus 1, somewhere on the board it was here written that this converges to the largest Jacobi exponent. On the other hand, this guy is a ball whose radius might shrink but with a sub-exponential level. So this guy here just converges to 0 almost surely. This is also a convergence which holds almost surely. Okay, so this stuff and that stuff is handled, only this stuff is not handled yet. But we can use this guy here. We can use that one. And how? We have not used so far that this new measure is self-affine. Right? Nothing, I just writing stripes and other nonsenses. How can we use this equation? Well, check what's the measure of this intersection. This intersected by the little transversal ball, pi. And let's use that this is a self-affine measure, so it satisfies this almost erased equality. So this guy here is the sum over all the probabilities pi and the push forward. Fi inverse of this intersection pbt. Let me not write all the parameters. But we assumed strong separation, right? This Fi inverse map would just shout out every part of the set out of nowhere, out of the part which is not seen by the measure, except one, exactly the one who corresponds to the 0th coordinate of that guy. Otherwise, everybody else has here 0 measure. So this is pi I naught of Fi naught inverse of this intersection. And what is Fi naught inverse? If I apply it, it's exactly my G map. This is what I said. On this cylinder, which corresponds to I naught, blow up it by the inverse of F. This is exactly the G. This is G of P intersected with BT, which we have seen that it's scaled exactly by that way. So we can replace here this guy, thinking back, we can replace this guy by the intersection of P and BT by just subtracting one iteration and multiplying it with the inverse of the probability. So this is exactly the same as saying Lyapunov exponent, this we already have, 1 over m, sum L goes from 1 to m, the logarithm of b sigma L minus 1i or L minus 1m. And this is how we define this R. That if you divide by the alpha symbol, it scales by that. So divided pi L minus 1, new measure of this little transversal ball at sigma L minus 1i or L minus 1n intersected with the cylinders.
Sorry, Balázs.
Yes?
How did you get rid of the other terms?
Because if this is my first coordinate, and to this point I apply the function who corresponds to that, it maps outside of the set. And here, my new measure does not live. So everywhere else, here, this guy is a subset of my attractor, if and only if this I corresponds to the first symbol of my cylinder. Otherwise, it's just 0. Okay?
Because BT is from the sequence I.
Yes. Okay, we are almost there. This expression is still not uplifting, but at least we have the log of pi L minus 1, right? Or, sorry, it should be a minus. And we know that by this will converge to the entropy. So at least again we have out of this disgusting large sum a part which converges to something which makes sense. So here we know that it will converge to, that part which includes only this guy, to the entropy of mu. I mean, since there is no minus, the minus the entropy of mu. What this other ugly term is doing, well, this other ugly term is handled actually by two powerful theorems. The first powerful theorem is the combination of the theorems of Hochman and Simmons. They say the following. This is not the Simon who was talking. There is the double M and other differences as well. Okay? So, it says the following. So, if we have a map from some nice space, I don't want to get into too much in the details, so that's why I'm just simplifying it from R2 to R, who is nice and say continuous and other nice stuffs, and you define a partition, actually a foliation of the plane by the inverse branches. Right? So you foliate your space along phi. Then you have a nice, again another nice measure, nu, and our measure is nice enough. Then there exists a unique, where the uniqueness, I mean up to a zero measure, set, unique family of probability measures, mu x psi, such that one guy here, mu x psi, is supported on my partition. On the other hand, for every measurable set A, this gives you the conditional measure of the measure nu on this stripe, on this foliation element chi. Furthermore, if you do the following, if you look at the ball around phi of x with radius r, and you look at the inverse image of that, and you normalize it back by this ball, inverse image of this ball, then this as a measure will almost surely converge weakly to the conditional measure. And not only almost surely, but if you are nice enough, and our measures will be nice enough, it happens also in L1. Yes? Yeah? So everything is fine so far, and what do we see here? What we see here, that if you let n goes to infinity, what do you see here? What is this tiny transversal ball? This is the stripe. What is the stripe? Exactly the same kind of ball, where you replace the phi with the orthogonal projection. So this guy here, this is what Simmons say, that this will converge. This part, these two green are not very much distinguishable. Let's try with a blue one. Okay, that's much better. So that this part here, that part, goes to this conditional measure belonging to this projection there exactly of f sigma L minus 1 I. That will be pi of I. Okay, the measure sigma of the partition element by P, the conditional measure. But there is one slight difference, that if you let n goes to infinity, you have greater and greater sums, right? And somehow these radii and L, everything wants to change. But Maker's theorem is on your rescue, who just says that if you have a sequence of functions who is converging to another function f, almost surely, so it's Maker, almost surely end in L1, then if you take this kind of almost Birkhoff sum, from k goes from 0 to n minus 1, this will converge almost surely, and in L1, to the integral of your function f. Okay, you need ergodic measure, stuff like that, all these kind of necessary conditions. I did not give detail. But the good part is that the log of that function is in L1. You even need that the sequence Fn are uniformly in L1. So you have a uniform bound for them. And these guys, the log of that has this property. So basically, where you converge, where this blue part and the blue part's Birkhoff sum will converge, is the integral of the logarithm of the conditional measure at this point, pi of I, of the cylinder set of pi of I, and integrated by my measure mu. This is a very disgusting expression, and we didn't want to use it at all. This is just some kind of intermediate guy in order to find our final goal. Because what does this mean? By using the massive machinery of Rocklin-Simons Maker, we could actually show that almost every orthogonal projection of my self-affine set mu along a strong stable, aka along a Furstenberg direction, is exact dimensional, and this exact dimensional value is corresponding to some kind of value where this is calculatable, and this is evil. And we want to get rid of it. If my informations are correct, then Károly's next talk and the last 45 minutes will be about very, very similar thing like that, how to handle and how this kind of problem related to the dimension drop conjecture and the no dimension drop of self-similar measures. Anyhow, for us, we just need that this is an ugly, ugly expression. But we actually don't want to use it. Because now we will understand. Now we will understand the balls. Recall that this was my self-affine set. And what do I want to understand? A ball. Not any kind of ball, of course. Again, I will just choose a subsequence. So if my center is pi I, I'm a planar ball. This doesn't do anything with the negative coordinates, right? but I look at only how the radii, how the first n coordinates acting on the smallest contracting ratio, on the smallest singular value. And I multiply it with a constant delta, a little delta. This little delta comes from the strong separation condition. This little delta from the strong separation condition is the delta who says that the distance of two distinct cylinder sets is at least that much. So if I multiply that part, which is the strongest contracting ratio, the strongest possible, by this little delta, you can be sure that this guy will not intersect any other cylinder set, just the one who corresponds to the first n coordinates. So for first n symbols. So my measure nu of this ball with this radii corresponding to the first n symbol will be exactly this intersection. With the cylinder set who is corresponding to, let me denote, instead of P, let me denote it from 0 up to n minus 1, this refined partition, which is exactly the same partition, except that you are looking here for the first n coordinates, okay? Yeah. Okay, so the measure is the same. And look at here. Now I need just a slight cheating. Only just a slight cheating to say that actually this part here is almost a stripe. I can draw here, oh, I chosen that fine, containing the part which is inside of this ball, right? And also I can contain a stripe with an Fi who contains this part of the ball. And I blow up this stripe. What do I get? A big stripe, my original long stripe. So again, using the self-affinity, and I will be finished in a moment. Using the self-affinity, we could get that we see here the product of the probabilities times this transversal ball around sigma ni of the ratio of this ratio. Where again we use that along EI we are invariant. We can handle the length of the stripe along how it behaves EI. And you can say that, okay, but this is more or less what? This wants to behave like the local dimension here. What's the only problem? The only problem here is that this point, the center, is wandering around your set. That's an evil property. How can you heal it? Well, with my favorite way, shout out that Igorov help us. Because you say that, okay, we know that the local dimension exists. There is an Igorov set where the convergence is uniform with arbitrary close to 1 positive measure, but we even don't need that, we just need that it's positive measure. And then I look at only those ends, only that sequence where this point visits my Igorov set. And this is enough because I have a positive frequency. How often do I visit it? So the radii is still does not grow faster than exponential along these points of visits. And basically that's it. If you take the logarithm of it and you divide by alpha 2ai, then you can get back the formula which was taking place here. Okay, I think I already used 2 minutes from the break. So yeah, that's all for the first part.
Oh, 12:30.
Perfect.